30-ish minutes is to convince you that once binaries meet in the center of a galaxy, they will merge. And so I'm going to go into a lot of background. I will go into some of the work that I've done and my group has done recently. And then those of you in the know who have read Archive, I'll talk about a slight little controversy at the end, so stay away to the end. The weird thing about this talk that I always feel very strange about is that I'm going to be covering some of the work that is done by experts in this room. So I feel a little bit weird about that. I hope I haven't forgotten to cite anybody. If there are questions, feel free to ask. They might be answered by the people who actually get the word, though. So be prepared to ask questions. Okay, so let's thank you to Mike. Let's give a big thanks to Mike for starting us off on this whole dynamical concept of how you bring black holes together. Talked about the dynamical friction phase, where the two black holes are in their separate galaxies. Here's an example, a famous example of that in UGC 6240, where these two black holes are separated by about a kiloparsec. They're not bound. Here's an example of a galaxy where the next stage happens. They have met, and they are a binary. The separation is about, I think it was 8 parsecs here. And this phase is mediated by 3-body scattering. That's the dynamics that brings the black holes to the next phase. And here is galaxy awesome, where the two black holes are close enough that they get closer by gravitational radiation. And we all hope to see that someday. Okay, so I'm going to give you a brief little review of 3-body scattering. And during that phase, the big deal is that the black holes meet and become hard at a certain radius, a certain separation. That separation will be called A throughout this talk. And for 10 to the 8 solar mass black holes, that's at about 10 parsecs. And then the way in which the black holes get closer is by 3-body scattering, stars that come within about 3A from the binary. And that star gains energy and angular momentum through the process. When the binary is hard, gets flung out of the galaxy, or at least to very large distances. That takes energy and angular momentum away from the binary, and the binary gets closer. And the kicker is that process is supposed to take over a Hubble time. And the punchline is that is true for a static, gas-free, spherical galaxy model at equilibrium with permanent ejections and no resonances, etc. So I'm going to break this down and show you a more modern look at the problem. All right, so in the 3-body scattering regime, the separation between the black holes, this is an astronomer equation, so they tell you what units they really want here, depends upon the mass of the black hole and velocity dispersion of the neighboring stars, because you got to interact with stuff. And for a 10 to the 6 solar mass black hole, that's about 0.1 parsecs. So just a common conundrum that I get is that folks think that the final parsec problem really is the fact that black holes can't get closer than a parsec. And that's not true. I'll show you a plot where we get that term in a second. But what it just means is black holes can't pass through the 3-body scattering phase. So these black holes, 2 10 to the 6 solar mass black holes, become bound as a hard binary at 0.1 parsec. And that time scale for coalescence, so to move into the next regime, is pretty quick. So this is, astronomer equations always tend to put the units that they really want in front for typical values. So for a 10 to the 6 solar mass black hole, typical stellar galactic densities, typical velocity dispersion of our Milky Way, Q is mass ratio. You get coalescence in a couple million years. That doesn't sound like a problem. If only we could keep the loss cone full. I'll explain what I mean by that in a second. Then you would get coalescence of these black holes in an astrophysically super short time. So you go from this phase to this phase, and that occurs at about a separation of, oh no, they've given me different units here that they want me to use. They want me to use a 10 to the 8 solar mass black hole. I refuse. So this happens at 10 to the -4 parsecs for the black hole that we were just talking about. So you need to mediate about 3 orders of magnitude of shrinkage before you can actually go to the gravitational wave regime. And this annoys me, because remember I said astronomers love to put the number that they really want you to have out in front? This is 50 billion years, so that's not right. So what this equation really means, and I was too lazy to change it, is how long it takes the black holes to decay by gravitational radiation only once they're at the binary hardening radius, because look, they've got AH in there. That's really, really large distance. So if we put the right numbers in, the separation that you really get once gravitational radiation takes over, this merger timescale is 1,000 years for two equal mass, 10 to the 6 solar mass black holes. So super short timescale. If only we could get to that gravitational wave regime, and what we need to do in that case is to keep pumping stars to the center. Oh Lord, what did I do? No.
Who is they that give you these numbers?
They is living reviews and relativity. This is, yeah, I don't know why this happened, but this is living reviews and relativity. These, I think I did myself because I wanted to try and do 10 to the 6 solar mass black holes. And then I got lazy because it was too big. Sorry, just grab it. Okay. Any more questions so far? Oh no. I mean, oh yay, questions. I'm so scared. Did I do the math wrong?
No, that's not what I'm saying. I was just, so the T of 1,000 years is very short, like you said.
It's super short.
So, I guess I'm confused. I mean, I thought the separation you're interested in is just how far apart are they, by, when time scales less than like a Hubble time or something. I don't know. What does that 1,000 years represent? What is the distance of the 1,000 years represent?
This is when the black holes are this distance apart. So
when
in
they're
other
that distance apart, it only takes 1,000 years to merge.
Yeah, that's right.
Well, what's so special about that distance then?
Because this is the distance where gravitational radiation starts to dominate over the three-body scattering phase. So in other words, when gravitational radiation starts to drive the evolution of these black holes.
And why wouldn't it, you think if the gravitational wave timescale is 1,000 years of that separation, the gravitational waves would dominate earlier on than that? Otherwise, no? I guess, well...
And gravitational radiation is a strong function of the frequency.
Okay. The important point I want you to take away, rather than specific numbers, is that the time scales for coalescence of black holes that are Milky Way type black holes, let's say, is not astrophysically long at all, if we could keep the loss constant. Okay? So if we could keep flame stars towards that binary, we would be golden. The problem is, this classical problem, which is represented in this famous figure, is that once you deplete stars that are in the loss cone, meaning the stars that can possibly interact with this binary, then the only way you can refill the loss cone in that static, spherical, isotropic galaxy, blah, 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 that I just talked about, those specialized galaxy models, the only way you can refill that loss cone is by two-body relaxation. And you all know that two-body relaxation is a very long time scale for galaxies. Galaxies are collisionless systems. You're not going to refill that loss cone on a time scale that is shorter than a Hubble time. So you throw out as many stars as you possibly can in that loss cone. You do it all. You empty the loss cone. The binary shrinks by a factor of about 10-ish, but that's not enough to get you to the gravitational wave regime. Okay? So the binary stalls at whatever distance it takes to remove that all of those stars. Does that sort of make sense? Here's that famous picture that I was talking about. Begelman, Blanford, Rees Nature paper where they described this. Their original black holes binary that they considered was a 10 to the 8 solar mass black hole hanging out with a 10 to the 7 solar mass black hole. Dynamical friction phase here for that system is about 100 parsecs, and then three-body scattering takes over. And if the loss cone were, oh gosh, sorry, I'm shaking, I must be nervous. If the loss cone were depleted, then the time scale to get to the next phase goes past the Hubble time, okay? And that occurs at about a parsec. This is the shrinking time scale, I guess you could say, the hardening rate, for gravitational radiation. So this time scale is short here. If you could refill the loss cone, then you would have astrophysically realistic time scales for mergers, even for those larger black holes. So this was the final parsec problem. Okay? You just deplete energy in this range, or sorry, you deplete stars in this energy and angular momentum range called the lost cone, and it can't be filled quickly. So the worst case scenario, actually, let me just step back. That was a problem. And so for the intervening 25 years, folks would do more realistic spherical static models with higher particle numbers to try and see if they could get the answer right. So in other words, get enough stars in the lost cone to be able to interact with the binary to allow them to merge. So fancier types of models, fancier types of simulations attempting to solve this problem, all in the spherical case though. Here is a synopsis of the problem. And what this is the coalescence time scale for black holes with a certain total binary mass. So this is a Hubble time. And this is 2 equal mass 10 to the 6 solar mass black holes. And their coalescence time is essentially a Hubble time. So for every black hole that we knew about back in that day, there was a problem getting the black holes to merge. The timescale for the merger was longer than Hubble time. Okay. All right. The deal that I want to convince you about over the next little bit is that the models that we used and the processes that we all used as a community were very, very idealized. So we made, because we wanted to understand the dynamics, the simplest possible unrealistic galaxies. And once we add degrees of realism to our galaxy models, we solve the problem. Okay? So let me just walk through some of the things that people have added to our more realistic galaxy models that help mediate this final parsec. So mediate through, help shepherd the black holes through the three-body scattering phase. And I have, because I'm the speaker here and I get to, I tell you my opinion about how important they are over the whole ensemble of mergers for every galaxy by the size of the box. And if you want to argue about how big the boxes should be, knock yourself out. I know some authors who are in this regime who are super upset that their box is small. So they get mad. I can make things small. All right, so the first one, and the most important one, is that very few galaxies are devoid of gas. All the models that were built thus far used stellar dynamical processes, and stellar dynamical processes only, to allow the black holes to get closer. But galaxies are gas-rich, and they're particularly gas-rich at high redshifts. And so this was a lovely Nature paper by Lucio Meyer. This is a gasoline code, Jillian's code, but it's not as fancy as hers. It includes black holes, but it doesn't. She totally fixed this to be a little bit better, to be lots better. This code had 2 equal mass galaxies. Oh, sorry, Lucio. It was really great. But I don't mean to okay, so it was awesome, and what it is 2 equal mass galaxies. Each galaxy has 10% of its mass in gas, not bad. And what they found is that the black holes frict against the gas too, not only the stars. They lose energy and angular momentum to the gas, and that allows the black holes both to pair, so it makes the dynamical friction time scale faster, and it gets them through this 3-body stage down to the smallest resolution element that they had in the simulation of the day, which is about 10 to the minus 2 parsecs, I think. That seems small, but I think so. That's still not the gravitational radiation regime, but it's the best you could do of the day. Now, some small caveats. This model, awesome, doesn't have star formation feedback and doesn't have AGN feedback, both of which will remove high density gas. So the effect might not be as dramatic as what these initial simulations show. But still, what we learn from this simulation is when you have gas, and when that gas sticks around, it's going to help the black holes get close.
So,
Yes.
a question about that.
Uh-huh.
So, you need an amount of gas that is as massive or more massive than the
I'll talk
sun.
about that in a sec. Absolutely.
Okay, good.
Yeah.
I'll wait for you
This-
to comment.
This is in the mass, sort of in the global galaxy phase. I'm going to zoom in to show you nuclear disk simulations in the next little slide. So this was also done by folks who zoomed in, and these are some of the folks who did that. And if I remember right, so again, equal mass black holes. And this is a zoom in simulation just of the nuclear region. Again, no star formation nor AGN feedback, actually no star formation, much less feedback or AGN feedback, but that's fine. It's an initial really well done run. And these black holes, I think, also don't get to the gravitational wave regime, but they certainly mediate another order of magnitude. So again, better than any other study has ever done. The problem, as Cole very intelligently pointed out, is the amount of gas that you need in this region to mediate another order of magnitude, to get the black holes another order of magnitude closer, is about 100 times the mass of the binary black hole in this simulation. There's a question about whether or not the nuclear regions of galaxies have that much gas. Still, when you have gas, black holes get close. So, sum up here, as long as the primary is gas-rich enough, and as long as the secondary isn't too light, gas is a good way to pair the black holes and navigate the final parsec. Okay? So, does gas solve the final parsec problem? I'd say yes, with some little caveats here about we still have some work to do to consider the effects of AGN feedback, star formation feedback, etc. Okay? Okay, I'm not going to go through all of these, but I do want to talk about the next one, which is this, shape. And along the way, I'm also going to touch on a bunch of things kind of accidentally because of the way the field went. So this is a sort of historical view here, where historicals the past, 5 years. So now let's start to think about shape. The cool thing is once you break spherical symmetry in a potential, even a little bit, even to 10 to the minus 4 in triaxiality, then orbits in that potential don't have to conserve angular momentum. They conserve energy, they don't conserve angular momentum. And so the consequence of that is that you get really awesome orbits. They're so pretty. Here are resonant boxlets. That's a pretzel, because it looks like a pretzel. I think that's like a 4 to 5 or something. I'd have to go count, and I don't think I can. There are also proper boxes where that formally have 0 angular momentum and can go straight through the center. There are tubes, beautiful tubes in triaxial galaxies, and there are chaotic orbits here as well. These orbits, since they don't have to conserve angular momentum, can whip through the loss cone. Right? On time scales, that can be short, much shorter than the relaxation time. So in this concept, we have the loss cone is full, and I sort of like, it's not the right thing to say, but I sort of think of it as the loss cone can even be over full, because what matters is the amount of stars on orbits that are radial. Okay? And you can have a lot of those stars on that orbit. Certainly many more stars on those types of orbits than in a spherical system. Okay? We'll come back to that in a little bit. But what I want you to take away is that you can keep a loss cone full in a triaxial galaxy. Okay? And another small thing to keep in mind is that the amount of stars that interact with the binary black hole depends intimately on the orbits in the model, okay, in the galaxy. Okay, blah, I just talked about all that stuff. Site, excellent people. All right, other sort of improvements to models. If you rotate a triaxial galaxy, still in equilibrium, no gas, nifty thing is you get more chaotic orbits than if the triaxial galaxy were sitting still. This is the orbit fraction as a function of energy. So this is close to the black hole, far away. So you start to get 30% of the orbits close to the black hole are chaotic. But if you rotate that thing, if you spin it, basically 40% of the stars all the way across are chaotic. Chaotic orbits go through every part of phase space that they possibly can, so they're certainly going to go through the lost time. Bless you. Okay, so this was first noted, as far as I can tell, by you in 2002, and what we've done is talk about a bunch of logical arguments. None of those were simulations, they were just thought experiments and proofs of principle and analytic studies and Fokker-Planck studies that show that this, in principle, could solve the final parsec problem. Until about 6 years ago, when this group was trying to study rotation. Remember, I showed you some rotating models? They stuck 2 black holes in it, and they created a model that was really highly rotating. And in fact, it was rotating so quickly that it was tumor ray unstable, meaning plonk, it collapsed into a bar, a rotating triaxial ellipsoid. And in the throes of that rotation, these black holes went to the final parsec. In other words, they got as close as they could in compared to the resolution, and that was appropriate to allow gravitational radiation to take over, blah. So I want to show you these figures because they're important, and I'm going to show you these types of figures over and over again. Here's a spherical model. So what you're seeing is 1 over A. It's basically inverse of the separation. So this is super, super close, far away, as a function of time. And what everyone will do is they will take their model, in this case it's a spherical model for comparison, and they will populate it with different numbers of particles, and then they'll track how the black holes evolve. And what you're seeing here is that the black holes are getting close. In particular, if you populate the galaxy with just 25,000 particles, it zooms close together. But what you're seeing there is not physics. What you're seeing there is artificial two-body relaxation from your computer simulation that are tossing the orbits every which way, including through the lost time. Okay? So when you see this spread, it is not physics, don't pay attention. Okay? The cool thing is in the triaxial simulation here, well, you see n independence. A little bit of difference here, but this was the first time folks did this, so this is an incredible difference from here. And so what you know here is that you're starting to see some of the underlying physics of real 3-body scattering, real lost cone refilling by actual numerically appropriate orbits. Okay? One problem with this, just to take a step back, is that this galaxy was in the throes of collapsing, and these black holes met on a highly eccentric orbit, and it made a triaxial system. So just to be picky, you don't know which of those things was most important here. But the nice thing that you see is that there is a mechanism to solve the final parsec problem just with stars. Okay? And by the way, that's important because not every galaxy is that gas rich. In fact, elliptical galaxies, well, they've got some gas in it, but they certainly don't have gas to the degree of the simulations that we've run. And in particular, for the high mass black hole range, like for the ones that folks want to see in pulsar timing, they typically set in massive galaxies which are predominantly ellipticals and gas poor. Okay? So it's good for us to still try and solve this problem just with stellar dynamics. Plus it's a cool little physics problem. So, all right, so continuing on that idea, folks finally simulated non-spherical galaxies, and they got black holes to merge. They tried to make a triaxial galaxy here by slamming together 2 equal mass galaxies on a radial orbit, and that makes a triaxial system. Now again, it's super time dependent because you're making a galaxy that it's a merger, so the potential is changing rapidly. But again, here's a 1 over A versus time for these spherical models, and look at that divergence here. And you start to see here some of the lines overlapping each other. This is for the lowest resolution run, I'm sure. And so this tells you a little bit about the physics. So there's this, in this case, there was also no problem. Again, it was two equal mass galaxies merging together in order to make a triaxial model. So we don't know which of the things contributed. Oh, shit. Oh, okay, sorry.
That was a citation.
Sorry. Okay, so here is equal mass merger remnants on eccentric orbits, not perfectly radial orbits. Yay, and independence, that's beautiful. And I love this paper because they talk about timescales, which is what we need. So here is how long it took those black holes to merge here in log space, and as a function of the mass of the binary. So 2 10 to the 6 solar mass black holes, 10 to the 7 years to merge, 10 to the 8, 10 to the 7.5, or 10 to the 8-ish. Another cool thing is to talk about the eccentricity of the orbits. This group found with their configurations that they often got highly eccentric orbits in the pulsar timing array band. So look out, you should see in PTA, if this model holds up, highly eccentric binaries. Okay? Same thing when you add relativistic corrections for the stellar motions. I'm going to skip that really quick because I want to get to my stuff in the recent controversy. Blah, blah, blah. So what we showed mostly in that section was that processes like rotation, bar instability, galaxy mergers, basically time-dependent potential stuff helped solve the final parsec problem. We also showed that post-Newtonian effects and resonant we didn't show that part, but resonant relaxation effects also may help as well. If you make your black holes have high eccentricity, your loss cone's pretty big. So if you can manage to do that, which there are ways, certainly, then you also solve the problem. Perturbations like GMCs and also minor mergers, tiny little satellites, may help as well. Third black hole is a really cool idea, but it just didn't happen very much, but we're going to come back to that in a second. Okay, so let's kind of test the limits. We're pretty confident that in most cases, every single one of those things, which are more realistic, progressively help the black holes get together. So in realistic galaxies, I don't think we have to worry, but we're stellar dynamicists and we want to play with toys. So we want to figure out exactly what is helping in good detail. So we made a sort of limiting case, a galaxy that was axisymmetric, gas-free, in equilibrium. Okay? We're going to see if the final partial is solved in that one. We made that kind of galaxy by adiabatically squeezing a spherical model, letting it rest and making sure it's stable. And then we ran the model using a directed body simulation on a GPU. And what we found was this. We ran a bunch of different flattenings, a bunch of different particle numbers, blah. Here are low particle numbers. And then once you reach above 500,000 up to 1 million particles for this flattening, we saw in independence. And once we passed that final hardening rate over to an analytic equation, we could estimate how long the black holes would take to merge. So 2 10 to the 8 solar mass binary black holes would take about 2.5 billion years to coalesce in this very idealized equilibrium, axisymmetric, not very flattened galaxy. And the eccentricities we found were about 0.2-ish, which is not small. And that was just this year. Also, the two lead authors are untenured. Thank you. All right, so we are working on something right now to figure out why this is happening. So we enlisted some of our team to look at the orbits inside these galaxies. They're in-body galaxies, but we can analyze the orbits, and we found these awesome orbits called saucers. So these are the top view of the saucer, and then this is the side view of the saucer. These are centrophilic orbits in an axisymmetric galaxy, and 60% of the stars in the inner 100 parsecs are saucers. So there's plenty of mass to interact with those black holes. That will be published eventually, but grad student is PR. Then last week, I got an email from Dave Merrick, who has a paper on archive. And he was interested, I think, in what we were studying. And so what he did was he made an axisymmetric galaxy with with flattenings up to 0.8 C over A, so not 0.75, but 0.8, in an isotropic system. So he didn't squeeze, he just sort of made an isotropic system. He pinned the black hole to the center, ran with n-body, direct n-body. There's some other details I can talk about, but the point, I'm sorry, almost done. The point is spherical, oh my goodness, look at that divergence. Axisymmetric, holy crap, even in triaxiality. He is not seeing physics here. So he's getting that the black holes are closer, but not from physics, from three-body scattering, from numerical relaxation. So also he gets the hardening rates for, are you nodding at me because you're mad at me? Okay, you're going to talk in a little bit, okay. Hardening rates for this isotropic equilibrium system are slower than the full loss cone rate, and are a factor of 3 smaller than what we got, which was for a full loss cone. And worse, they have numerical relaxation all the way through. So what they are suggesting is that anybody who wants to do this study better use more than 1 million particles. So, am I worried? Not really, kind of, yes. A little, not that much. Okay, so let me just tell you the response of basically everybody. Fazile's most concerned about the fact that his black hole wanders, so he drops the black hole from a for a realistic way, and so he gets an n=1 mode that basically lets the black hole wander around. The other simulation kind of pins the central black hole to the center and drops the other black hole in a circular orbit so that there's no wandering of that black hole. I think the deal is when we squeeze an adiabatic model, we make radial orbits by squeezing. That's what you do. So we make our model and it's stable, but you can populate a certain shape with any type of, not any type, with a non-unique variety of orbits. And we happen to have lots of radial orbits in our model. And also at the very center, we have a teeny tiny bit of triaxiality. I know that because I saw a pyramid, which only occurs in triaxial systems. So it's itty bitty tiny, like I think we have C over A of 0.75 and B over A of 0.99. I would have called that spherical. I called that, or in that direction. But apparently we got a pyramid. So Reiner said, hey, they only did the experiment to 0.8, and we didn't really see the final parsec problem solved until we went to 0.75, so I don't really get why with their beef here. And Peter said the same thing, okay? So it doesn't look like we're all extremely worried, but you know what? Having an excuse that much usually means that you're a little worried and should probably do the experiment with more particles or share the same model or that sort of thing. So stay tuned. But the big deal is that this is a pedantic argument at this point, right? Because really, each galaxy is not going to be an equilibrium, static, gas-poor, very tiny little bit flattened axisymmetric system in the first place. Real galaxies are dynamic. They are certainly more flattened than what we showed. They have gas in them, etc. So real galaxies experience many perturbations that allow the black holes to merge. In reality, the final parsec problem shouldn't exist for any system. Okay? But we still want to know the details. So we'll still work on this. So where do we know? I said it shouldn't happen for any galaxy. But there is a case that I can think of. Maybe you guys can think of others. If you had a gas core, isolated, perfectly spherical and isotropic, low-density, massive galaxy that's accreting a teeny tiny dwarf galaxy on a circular orbit, the black holes won't merge. Okay? But then it's because of dynamical friction. So there's some more things to think about. Those billion-year timescales for the mergers that we got is kind of long. Maybe you get a third black hole in by that time and have 3-body encounters then. We need to add these sort of hang-ups, these actual merger times, to semi-analytic models, etc. And the big thing is that we need to start to calculate merger timescales for a realistic suite of galaxies. That's all I've got. Thanks, everyone.